In this session, we're going to go over the repeated measures in ANOVA. And so I've got an example here to work through this with you. In essence, the repeated measures in ANOVA, if you look at how the variance is broken down, so this is our total variance for the study. Remember, the total variance, this first part here, is just like what we did with a one-way ANOVA. We calculate our total variance, which was basically getting the variability among all these scores here, and then we break that down between for the between treatments, the differences that exist between the means here, and the within treatments, the differences within each of these groups, which we would get by the sum of squares here for each of these. What's different is with the repeated measures is we break it out now to look at individual differences as well. We're able to tease that out and then have what's left over is what we call our error variance. So in this formula, we'll be taking the between treatments and dividing that by the error variance to get our F ratio. Now, that part is what's different compared to the one-way ANOVA. So if we have a set of data here based off of a study that was actually done over at Hope College looking at the physiological effects of how it is that people respond to a hurt that somebody has done to them. And so you imagine being in this study, you're asked to think about a time in which someone has hurt you in some way, and then you're hooked up to galvanic skin response, blood pressure, heart rate, and that we're getting your physiological responses as you think about what it would be like to forgive the individual, and they're giving your physiological responses to that, to have empathy for the individual, to hold a grudge against the person, or to harbor the hurt, to kind of hang on to thinking about how the person has hurt the individual. And so and then obviously within this design you counterbalance these different conditions. So we have each subject going through each of these conditions, and you're getting their physiological responses. And so let's imagine this is very simplified data that has the negative affect, if you will. So the lower the score, the less negative affect. The higher the score, the more negative affect. And you'll see that we have differences here, individual differences. Some people have more negative affect compared to other people in terms of their physiological responses. And then you'll notice we have by condition. We can look at the means as well by conditions. And you'll see here for the forgiveness and empathy seems to be lower mean responses, lower negative affect when they respond in this way as compared to when people think about holding a grudge towards a person or thinking about how the person has hurt them. Here we've got the sum of squares is just the variability that exists within each condition. So this part is all the same as what we did in the one-way ANOVA. That's what we would see in the one-way. The difference is this person totals, which are these individual differences. You'll also notice a difference here in terms of sample size. We have 5 subjects. That's a lowercase n sample size. But we have 20 scores. Okay, each of those subjects created 4 scores for us. So we have 20 scores. That's our capital N. G is the same. It's just if we add up all these different scores, it adds up to 55. K is the same, so the number of conditions that we have, and that's 4. And then what I've already done for us here is taken each score, squaring it, and adding it up. That sum of x squared piece that we do for the first part of the sum of squares formula. So let's look through this quickly of how you would calculate the sum of squares for each of these. So for our total sum of squares, that's what he's saying. We take each score, square it, and add it up. When we do that, we get 243. And then our G is 55. That's just adding up each individual score here. It's to be 55 squared divided by, and then this is the capital N, so the number of scores that we have, 20. Okay, so 55 squared divided by 20 gives us 151.25, 243 minus 151.25, that's the 91.75. So this is all the variability in this study. Okay, now we're breaking down that variability into its various components. So next part, we could figure out the within treatments. Sum of squares, this is just like what we did with the one-way ANOVA. It's quite easy. We just take the sum of squares within each of these conditions. So 6 plus 8 plus 8 plus 6. We add that up, and it's 28. So our sum of squares within is 28. And our sum of squares between, remember there's two ways in which we can calculate this, the easy way and the hard way. The easy way is just 91.75, the sum of squares total, minus the sum of squares within of 28. So 91.75 minus 28 gives us 63.75. Okay, so that's the variability here for the t's. Okay, for our totals or for the means as we saw it before. Okay. So we've got our sum of squares between, sum of squares within, our total sum of squares, just like we calculated with the one-way. This is the different part here. Now we're going to calculate the person totals. How do we do that? We're going to take each one of these, we take that person total, 9 squared, divided by the number of scores that created it, or the number of conditions, 4, plus 19 squared, divided by 4, plus 7 squared, divided by 4, plus 8 squared, divided by 4, plus 12 squared, divided by 4. I just took each one of those person totals for that. We're going to add all those up, and then we'll subtract out this part. There's g squared divided by 20 that we calculated once before. So 9 squared divided by 4, 20.25 plus 19 squared divided by 4, 90.25 plus 7 squared divided by 4, 12.25 plus 8 squared divided by 4, 16 plus 12 squared divided by 4, 36. We add those all up together. Plus the 16 plus 36, and we get 174.75. So 174.75 minus, and then 55 squared divided by 20 minus 151.25. 174.75 minus 151.25 gives us 23.5. Okay, that's our sum of squares for the person totals here. Next is we want to figure out the error. So the sum of squares error, how we calculate that is we take our sum of squares within that we calculated. Our sum of squares within that we calculated, if you remember, was 28 minus the 23.5, and we got 4.5 for our sum of squares error. This, eventually when we calculate the mean square for that, that's what we're going to divide the sum of squares between by. The other some of the degrees of freedom as we work through this. So the degrees of freedom for the subjects, between subjects, is n, the lowercase n, the number of subjects we have, minus 1. So our degrees of freedom there are 4. And then our degrees of freedom For the air, is our degrees of freedom within minus that between subject. So we already got this one of 4. Degrees of freedom within each group. So our degrees of freedom here, we have 5 scores minus 1. So that's 4 plus 4 plus 4 plus 4. We have 16 minus 4. So our degrees of freedom for the air will be 12. Now if we put this in our Anova table, all of our information in our Anova summary table, again, notice this first part is the same as what we did before. So this was 63.75. This was 28. And then we're breaking this down into its 2 components. The between subjects component and the within. So this, or excuse me, and the air. So 23.5 we had here, and 4.5. Notice these 2 add up to be 28. Okay, we're just breaking this 28 down into those pieces. So this means that out of that variability, we could attribute 23.5 of the sum of squares to the individual differences that we had. Our degrees of freedom, remember we had 4 treatments, so 4 minus 1 gives us 3. We already figured in our within treatments of 16, and then that was broken down by the between subjects was 4, and then our air was 12. Our total here then is 19. We had 20 scores, minus 1 gives us the 19. Our total sum of squares is here. Then to get our mean square for each of these, 63 divided by, no, 63.75 divided by 3, 21.25. And then for our within, what we really care about is the between subjects and the air. So we can do our total within, 1.75. 23.5 divided by 4, 5.875, and then 4.5 divided by 12.375. This is now for the F ratio, we take this divided by the air. You'll notice how this is going to be a very large F ratio. .67, massive. So, and this would certainly be statistically significant. The F ratio that we'd look up in the back of the book would be 3 and 12. Okay, those would be the degrees of freedom that we would use for that. So when 3 and 12 is the degrees of freedom. Here's our F value, 56.67. And then P is less than 0.05 for sure. It'd actually be less than 0.001 for this. In summary, for looking at the variability on this, if we look at it here, our total variability is all those scores there. We look at the means here for the between treatments variability. We look at those sum of squares for the within treatments, and we look at the person totals for the between subjects.